Hey, and welcome to the Explainer. You know, we've all seen it. How can a computer possibly beat a world-class grandmaster at a game as complex as chess? Well, it's not just about being a super fast calculator. There's a really clever trick involved, and that's exactly what we're going to break down today.
You might think it's some kind of supercomputer magic, right? Well, not exactly. The real secret is all about efficiency. It's about figuring out how to ignore millions or even billions of moves that are just, well, bad ideas without ever wasting time on them.
All right, so here's how we're going to tackle this. First, we'll look at the basic, but super slow, way of playing a perfect game. Then we'll introduce the smarter, faster way. We'll get into the rules, and then we're going to walk through two different examples, step by step, before we talk about why this is all such a huge deal.
Okay, so before we can learn the shortcut, we really need to understand the long way around. And that's an algorithm called Minimax. It's kind of the foundation for all of this.
So Minimax is designed to be a perfect player. It looks at every single possible outcome. Now, imagine you're the max player. You want the highest score possible. And you're playing against mine, who wants the lowest score possible. So let's look at the mine player's choices. On the left branch, it can force an outcome of 3, 12, or 8. Since it wants the lowest score, it's going to choose 3. In the middle, it'll pick 2, and on the right, it'll also pick 2. Okay, so now it's Max's turn to choose a branch. Max looks at what mine will do and sees its options are a 3, a 2, or another 2. Naturally wanting the highest score, Max picks the path that leads to 3. Simple, right?
Well, here's the giant catch. That works for a tiny tree, but a game like chess has, on average, 35 possible moves from any position. So imagine a tree where every node has 35 branches, and you go down dozens of moves deep. The number of possibilities just explodes. This is what we call exponential complexity. It's basically impossible to compute. You'd be waiting until the end of the universe for the computer to make a move.
So, if checking everything is off the table, what do? We can't just be perfect and slow. We have to be perfect and fast. We need a much smarter way to search for the best move.
And this is the core question, the big idea behind something called alpha-beta pruning. What if we could just chop off huge sections of that game tree because we can prove logically that they contain no useful moves?
To do this, we need to keep track of a little more information as we explore the tree. So let's meet our two new best friends, a couple of variables called alpha and beta. Okay, so think of alpha as Max's personal best. It's the best score that Max is guaranteed to get so far. It starts at negative infinity and it can only ever go up. Beta is Min's defensive line. It's the best score, meaning the lowest score, that Min can force on a given path. It starts at positive infinity and can only ever go down.
And this right here, this is the secret sauce. The magic rule is, we can prune a branch the moment alpha becomes greater than or equal to beta. Think about it. Let's say you're Max, and you've already found a sequence of moves that guarantees you a score of, say, 10. That's your alpha. Now, you start exploring a new branch, and you quickly realize that your opponent, Min, can force a situation where you get a score of 5 at best. That becomes the beta for that path. Well, why would you ever explore that path further? You already have a guaranteed 10. You just ignore that new path entirely. That's pruning.
All right, that's enough theory. The best way to understand this is to see it in action. So let's get our hands dirty and walk through an example, just like we're at a whiteboard. Okay, the search always starts depth first, down the leftmost path. So we go down, 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 and bam! We hit a final score of 3. Now, that number travels back up to its parent, the min node B. Node B now knows it has a way to keep Max's score down to 3, or maybe even lower. So B's value is at most 3. That info gets passed up to the top Max node A. A now knows it has an option that guarantees it a score of at least 3, so we set A's alpha value to 3. We keep exploring that first branch. We see the other options are 12 and 8. Now, since B is a min node, it's always going to choose the smallest number to pass up to Max. So out of 3, 12, and 8, it picks 3. The value of this entire left chunk of the tree is officially 3, so node A's alpha stays at 3. It knows it can get a 3, and now it's off to see if it can do any better.
Now things get really interesting. We move over to the second middle branch. We go down to the first leaf and see a score of 2. That number pops up to the min node C. Now think about what this means. Node C knows it can force a score of at most 2. So C's temporary beta value becomes 2.
And prune. This is the moment. Let's check our condition. Up at node A, Max has an alpha of 3.
It has a guaranteed path to a score of 3. Down at node C, Min is looking at a path that will result in a score of 2, or maybe something even worse for Max. Since Max's guaranteed score of 3 is already better than the absolute best it could hope for down this new path, which is 2, we cut the whole branch off. It's pointless to keep looking. A smart opponent would never let Max go down this path anyway.
And just look at that, we found the final optimal move is to go down the path that gives us a score of 3. And we figured that out without even looking at those nodes with values 4 and 6. We saved ourselves work because we knew they couldn't possibly change the outcome. How cool is that?
I know that can be a little tricky the first time, so let's lock it in. We're going to apply the exact same logic to a new, slightly bigger tree.
All right, here we go again. Take a look at this tree. We're going to do the same thing. Depth first search, left to right. Keep an eye on alpha and beta, and see if you can spot where we're going to be able to make a cut.
And here's the answer key. See all those nodes circled in yellow? We never had to visit them at all. Let's just trace the first prune. After we explore that whole first main branch, the root max node knows it can get a score of at least 4, so its alpha becomes 4. Then we start on the middle branch. The min node sees its first child, which has a score of 2. Right there, that min node knows its value is going to be 2 or less. And we stop. Since Max's alpha of 4 is greater than this branch's potential of 2, the entire middle branch, it's gone. We never even look at the other 5 numbers there. And the same thing happens on the far right branch.
So this is a neat little trick for small diagrams, sure. But why does this actually matter? What's the real-world impact of being able to do this?
The efficiency gain is, well, it's staggering. In the best-case scenario, pruning lets you search twice as many moves ahead in the same amount of time. It effectively takes the number of choices at each step, b, and reduces the problem to the square root of b. For a game like chess, that's like turning a problem with 35 steps into a problem with less than 6. It's a total game changer.
So let's just boil it all down. Minimax will always find the perfect move, but it's way too slow for complex games. Alpha-Beta Pruning is the optimization that makes it practical. It gets you to the exact same perfect answer, just way, way faster. And it all hinges on tracking alpha, Max's best score, and beta, Min's best score, and making a cut the second alpha is bigger than or equal to beta.
And hey, don't just take my word for it. This isn't just theory. This is exactly how IBM's Deep Blue computer beat the world chess champion. For Deep Blue, this pruning technique took the average number of moves it had to think about from 35 all the way down to just 6. That's an absolutely massive improvement.
And that leaves us with a final thought to chew on. This whole idea of setting a baseline for what a good outcome is, and then immediately discarding options that are provably worse, that's not just for an AI playing a game. It's a really powerful way to think about making decisions in business, in strategy, or even just in your own life.